Hi everyone, we are Group 2 and today we are excited to present our analysis on warehouse inventory management.
First, I'll explain the case we're discussing. A warehouse is facing difficulties in managing its inventory, leading to overstocking, stock out, and increased operational costs. To solve this issue, we need a system that can automatically adjust inventory placement and robot routing based on real-time order data. This system should balance storage efficiency, delivery speed, and operational costs. Additionally, it will integrate classical algorithms such as linear search, greedy algorithm, or brute force to enhance inventory management performance. Now let's see how computational thinking, specifically decomposition, can help solve this problem. First, we need to analyze the warehouse structure, including the number of storage cells and distribution zone. Second, we must identify key issues such as overstocking, stock out, and inefficiencies in good movement. Next, we determine the minimum and maximum stock levels for each product based on demand patterns. After that, we can classify product according to demand levels and shelf life. Finally, we evaluate the effectiveness of the current restocking strategies and look for ways to improve them. With this approach, we can create a more efficient and optimized system.
In this slide, we explored the role of pattern recognition in computational thinking and how it applies to warehouse operations. The process starts by analyzing historical sales data to identify product demand trends, which helps with forecasting and inventory management. Recognizing supplier delay patterns and estimating delivery time ensures restocking happens on time and reduce disruptions. By observing how storage space is used over time, we can optimize the warehouse layout. Additionally, analyzing how demand changes with season improves planning. Finally, identifying areas with high-frequency robot picking helps enhance efficiency by speeding up the picking process and reducing delays. In this part, we begin by modeling key factors such as product demand, storage capacity, supplier lead times, and operational cost. These factors play a critical role in decision-making, especially in warehouse operations. Next, we calculate the optimal distance between storage locations and picking zones, which enhance efficiency and ensure quicker access to inventory. Additionally, we simplify the representation of order data into a format that is easily understood and processed by algorithms, streamlining workflows and improving data processing accuracy. Simulations are also created to test and refine storage strategies by mimicking real-world scenarios, helping us evaluate the effectiveness of various approaches before implementation. Finally, machine learning-based prediction models are developed to forecast demand, improving the accuracy of restocking schedules and preventing stockouts.
Now, let's discuss the algorithm used to optimize the warehouse operations. First, calculating optimal stock levels. The first step is calculating the optimal stock levels. This is based on the demand data and supplier lead time to ensure that we maintain adequate inventory while avoiding overstocking. The second one, determining efficient storage location. Next, we determine the most efficient storage location. This is by considering the robot access speed, ensuring that the robots can pick items quickly and efficiently without unnecessary delays. Third, using greedy algorithms for path selection. The algorithm uses greedy algorithms to select the shortest path for robots when picking items. This minimizes the time span navigating the warehouse, improving operational speed. Fourth, minimizing operational costs. We also focus on minimizing operational costs by automatically adjusting restocking patterns. This ensures that we only restock when necessary, optimizing warehouse resources. Next, improving system response to demand spikes. Lastly, the system is designed to handle demand spikes by using brute force simulations for worst-case scenarios. This helps improve system response and ensure that the warehouse can manage large surges in demand without compromising on performance. This algorithm is key to improving the efficiency of warehouse operation and ensuring that goods are picked up and delivered in the most cost-effective and timely manner. Next on the flowchart process of optimizing the placement of goods in the warehouse using data-driven techniques and robotic automation. First, we start and the process begins with collecting historical data related to the stock patterns and past transactions. This data is essential for identifying trends and patterns. Next, data analysis and stock pattern identification. In this step, we analyze the historical data to identify stock patterns, which are crucial for the understanding how different goods move within the warehouse and at what frequency. Next, determining placement based on the data analysis. We then move to the placement phase, where we decided the optimal location for each good. This step aims to minimize retrieval time and improve operational efficiency. Next, determining optimal placement of goods. Once the placements are decided, we determine the most efficient layout for the warehouse. This includes evaluating factors such as shelf placement, proximity to frequently ordered items, and ease of access. Next, reserve real-time orders. The system then starts receiving real-time orders from customer. This is where robotics comes into play, ensuring that the goods are picked up quickly and accurately. Next, robot navigation for picking up goods. Robots are then deployed to pick up goods from the determined locations, ensuring the faster and more efficient process. Next, updating stock after pickup. Once goods are picked, stock levels are updated in real time to reflect the change. This keeps the inventory accurate and up to date. Running restocking automation. If stock levels dip below a certain threshold, the system automatically triggers restocking. This ensures that the goods are always available and there is no delay in fulfilling orders. Next, evaluation of a system efficiency and optimization. Finally, the system performs in the evaluated. This helps to optimize the entire process, ensuring that the warehouse operation is efficient and cost-effective. Next, to the testing. Before the system is full operational, it undergoes testing to ensure everything works smoothly, identifying potential issues that need to addressing. So, in conclusion, this process leverages historical data, stock patterns analysis, and robotic technology to enhance the efficiency of goods placement and retrieval. By automating key steps, we can significantly reduce errors and improving the overall speeds of warehouse operations.
So on this slide, we have a simple plan for our warehouse inventory management system works. First of all, we set up the main variables like our current inventory and how much demand we expect, and the limit of our storage space. Next, we load all the important data. Then, whenever a new order comes in, we add it to our queue and update our inventory. After that, we check all of the items and check if any of the items' quantity is below a certain threshold. If it is, we place a restock order. Finally, we organize our inventory based on how often items are ordered, making sure popular items are easy to access. And this helps us keep everything running smoothly and efficiently. For this slide, this is the slide for the Big O notation, which is a way of describing how fast or slow an algorithm can be when dealing with larger amounts of data. For example, if we're sorting our inventory based on demand, it might take more time the more items we have. And by understanding the Big O, we can pick methods that handle big inventories efficiently, making our system faster and more reliable. Lastly, thank you for your attention throughout our presentation, and we apologize for any shortcomings in our presentation. Thank you.